Hey AP Calc students, it is time to take a look at another FRQ. This time it's going to be from year 2015 on the AP Calc AB exam, and it's FRQ number 3, which means it's a non-calculator question, and we're going to take a look what they're asking you to find. Now this particular style of question I can tell just by looking at the table that's given there. This falls under a category that I like to call table of values, and the reason is in the given information you get a table of values. So whenever you get this style of question, I strongly recommend just graphing it, and it's going to pay off here in the long run. But we'll read the question and then go to the graph. So the question says, Johanna jogs along a straight path. For 0 less than or equal to t less than or equal to 40, Johanna's velocity is given by a differentiable function v. Selected values of v of t, where t is measured in minutes and v of t is measured in meters per minute, are given in the table above. So not only is this a table of values question, but it's also a blend of incorporating position, velocity, acceleration, not uncommon for these types of questions. So the first thing, like I said, I highly recommend doing on these is just graph the table of values. Now, before you start drawing, you might want to notice here your x values, or independent variable t values, go from 0 to 40, and these are not equal distance apart. And I don't worry about making this graph to scale, you just want to get a feel for what's going on. The other thing you want to notice here is that the velocity is negative pretty significantly here at 24 minutes. So I'm going to come over here, and I'm just going to make a graph that's going to help me just see what's going on here. So this is time, and here is my velocity. And I'm going to say, well, if way over here, I'm just looking at from 0 to 40, so here's 0, I'm just going to insert 12, 20, and 24. So I'll call that about 12 minutes, and then this would be about 20, a little bit closer is 24, all right? And then the y values here, 0, 0, we have this value right here. At 12 minutes, we're up at 200. And again, I don't really worry about things being to scale. So that's 200. And then up a little bit farther at 12 minutes is going to be 240. And then this is this one that's negative. So at 24 we go negative 220. So I'm going to go down to here, negative 220. And then at point 40, or at 40 minutes, I'm up at 150, which is actually a little lower right here. All right, and so I'm actually going to just put a point at each one of those spots to see what's going on. It was 12, 200 here, and 20, 240. So on the table of values, the highest value they give you is 240 at the 20th minute, and the smallest is negative 220 at the 24th minute. Now, you have to make sure you don't assume these are the highest and the lowest values. It's just selected values. And what I'm going to do, just to give me an idea, I like to just make a dotted line that just sort of tells me kind of in general what's going on with this function. Again, I'm not sure if this is the minimum value, but this could be something that the velocity graph looked like. And it just gives me a feel for the question. And you'll see why how useful this graph is here in just a little bit. All right, so let's see what they want us to figure out. And by the way, I think the question makes sense. She's jogging for 40 minutes, and her velocity is symbolized here. And the fact that her velocity is negative here should be telling you something about direction if you've taken some physics. But it's fairly straightforward. Here's her velocity jogging for 40 minutes. All right, so let's go to part A. Use the data in the table above to estimate the value of v prime of 16. So I'm going to put A here, and here's what they want to know. Well, what they're testing you on here is, do you remember all of your rules regarding PVA? So I'm going to put PVA right here, and you want to remember that when it comes to position, velocity, acceleration, that you're taking the derivative as you head from position to acceleration. When you head from acceleration to position, you're going to be integrating. Very useful little tool to remember. So they want v prime of 16. Well, v prime of 16 is another way of saying they want the acceleration at 16. It's the same question. Well, the reason it says to estimate it, that's really important. The reason you have to estimate it is that you don't have the function. Now, if they wanted you to find v prime of 16, or the acceleration at 16 minutes, and they gave you the function, you would just take the derivative. But you don't have the function, you just have selected values. So in this type of question, the fact that they say estimate is a huge clue that you're going to be approximating using average rate of change. So this is actually, this little question right here, when you see it, you want to say, oh, that's an AROC. This is what they're asking me to find. They want me to find average rate of change. Or in other words, they want me to find Algebra 1 slope. Now, whenever you get this kind of question, they always do this. They always pick a value in the middle of an interval. And if you'll notice, they want A prime at 16. Well, if you'll notice right here, 16 is right in the middle of the given value from the table. It's 4 from 12 and 4 from 20. So what they want you to do is approximate the derivative, or the slope of the tangent. Well, the slope of the tangent would be there. We're going to approximate it with the slope of the secant. That's what average rate of change is. So all we have to do is use table values. It's a very easy question, but you have to understand the vocab. So what we're going to do is just do difference in y over difference in x. So we're using 12 and 20 as our values. So the velocity at 12 was 200, minus the velocity at 20 is 240. And then my x values there were 12 minus 20. Do a little quick simplifying there. We get negative 40 over negative 8, which is equal to 5. Now the number is 5, but you have to be really careful that we make sure that we get our labels correct whenever we're taking the rate of a rate. Now remember, velocity is a rate. Now we're taking the rate of a rate, so that means that our time is going to be squared. So this was in meters, so this is 5 meters per minute. But the minute is squared, because technically it's 5 meters per minute per minute. Okay? And that's question A. Okay? Now, let's move on. Letter B. Using correct units, explain the meaning of the definite integral 0 to 40, the absolute value of v of t dt in the context of this problem. And then it asks us to approximate it. Well, let's take a look at that and think about it. So they want us to say, or they want us to interpret, what is the meaning of this integral? Well, if we go back to our little sketch right here, if we're going to integrate velocity, we're going to get position, or a change in position. But you have to be careful on these, because sometimes your change in position could be 0. For example, if, let's say, you're at the starting line, and you run down a field and you come back, your change in position was actually 0. But if you take the absolute value of your velocity and integrate it, you're going to get your total distance. So if you remember, there's net change versus total change. And so when it's absolute value, you're accounting for all the distance you ran. So another way to think about it is, let's say you're a track athlete, and you're going to run a 400 meter. You're going to run 1 lap around the track. Well, if you run a full lap around the track, and you just integrate your velocity, your change in position is 0 because you finished at the starting line. However, if you integrate the absolute value of your velocity, you would get 400 meters because that was your total change in distance. So you have to make sure you have that down, that when you integrate absolute value of velocity, what this is representing is the total distance traveled, or in this particular question, this is equal to the total distance Johanna jogged in 40 minutes. Or from t equals 0 to t equals 40. Now, if it would have just been v of t, that's where you got to think. What would it have given you? The distance would have been, it would have been her change in position from in the 40 minutes, or from t equals 0 to t equals 40. So remember, your change in position is oftentimes different than your total distance traveled. Clearly that's going to be the case with this one because we have a negative value we have to deal with here. So now the rest of part B says to approximate the value of what we just did using Riemann sums with 4 subintervals indicated in the table. Well, the reason I wanted to make the sketch was I could anticipate that they were going to have me do a Riemann sum approximation. Sometimes it's a trapezoidal rule. And so what we're going to do is do Riemann sum approximations from here. And so since it's the absolute value, what I'm going to do, and it says to come from the right, so I'm going to use 40. And if you remember, I'm going to use 40 coming from the right. I will not wind up using 0. And if I was coming from the left, I would use 0, wouldn't use 40. So I'm coming from the right, so I'm going to need this to be an edge of one of my rectangles. Here at negative 220, because this is absolute value, all of my y values become positive. So just to highlight that change here, this becomes a positive 220, so that would be about right here. I'm just going to make that point right here just to emphasize that we made a pretty significant adjustment right here. And that was 220, and the reason we did that was we're doing absolute value. Otherwise, we would have used this value here. Then at 20, according to the table, we are at 240. At 12, we are at 200. 0, we're at 0, but we won't use that anyway. So we're coming from the right, so I'm going to sketch my rectangles. So there is my first rectangle. Here is my second one. Here is my third one, and I'm going to have to come down. And then there is my fourth one. Now make sure the 16 was inserted for question A, just for illustration purposes, so that wasn't relevant. So there are my 4 rectangles, and if it's confusing to you, you can definitely take this out of here now. If that little sketch of what the function looked like was confusing. And you can say, okay, well those are my 4 Riemann sums, and I have to figure out the area. Now even though this is a non-calculator question, they ask you to do a little multiplying here. Not a big deal. So I'm going to say, well, approximately from 0 to 40, using this method, so I'm just going to set this up here. I'm going to say it is approximately, and I'm just going to look at my 4 rectangles. Now I'm going to start at the right because they said to do a right-hand one, and I'm going to look at my width times my height. So the width from 24 to 40, this is going to be 16. So the first rectangle is 16 times the height, and the height at 40 was 150. So I have 16 times 150, plus the next rectangle over, 20 to 24, is only 4 wide, and then the height is 220. So I have 4 times 220, plus my next one, 16 to 12, this width is 8, and my height is 240. And then my next one here, my width is 12 and my height is 200. Okay. Now once again, it's always going to be emphasized that integration is represented geometrically by area under the curve. We're integrating the velocity function, or approximating it actually, with our 4 Riemann sums. So now we just have a little tedious math to do here. And so 16, what do we have here? 16 times 150, that's going to be 2400. Plus 4 times 220, that's going to be 880. Plus what do we have here? 8 times 240, that's going to be 1920. And then 12 times 200 here, we're going to have 2400. Oops. 2400. And if we add all of those up, we're going to get 7,600 meters. So that was the total distance traveled by Johanna in the 40 minutes. It was 7,600 meters. So it said, using the units, explain what this means. Her total distance traveled in the 40 minutes of jogging. And approximate it using Riemann sums. So that was her total distance. So this would mean the fact that one of these velocity was negative direction-wise. That means she was probably jogging on a trail that went back and forth. And so because of the negative velocity, it would make her change in position seem less, but her total distance traveled is more. So there's part B. Let's keep going. Part C. All right. So part C says Bob is riding his bicycle along the same path for only 10 minutes from 0 to 10. Bob's velocity is modeled by this very basic cubic function. So they actually give us Bob's velocity function, and you'll notice, since this is not a calculator question, it's a very friendly polynomial, and they say it's t cubed minus 6t squared plus 300. And what they want to know is, and they say t is measured in minutes, just like Johanna's jogging, and it says b of t is in meters per minute, and they want to find Bob's acceleration at time t equals 5. This is the easiest question so far, actually. Going back up to here, they want Bob's acceleration. Well, we just need to take b prime. So first we'll take the derivative. Nice friendly power rule here. And then we need to evaluate it at 5. So b prime at 5, this is going to be 75 minus 60. And we're going to get 15, and it's going to be meters. And again, it's acceleration, the rate of a rate, so it's going to be meters per minute squared. All right, now we're ready to wrap it up. Part D. Part D says, based on the model B from Part C, find Bob's average velocity during this interval. Well, what they're testing you on is, do you know the difference between average rate of change versus average value? Now, earlier in the year, we went over average value, and the average value of a function, just to write this here as notes, I like to include some notes here as we're doing the question. So the average value of a given function, so I'm just going to call it f. Okay, the average value of f of x is equal to 1 over the interval that you're evaluating it at. So the average value, which is not the average rate of change, they asked that earlier in the question. This was an AROC question. But over here, the average value of any function is the integral of the function over the interval times 1 over the difference of the interval values. So 1 over b minus a times the integral of a to b of f of x dx. So this is actually what they're wanting you to do, is figure out the average value of Bob's velocity, and they're going to see if you make a careless error. Now, what's very easy to do is to think you're finding average value or a rate of change, and so you think, oh, they want the acceleration, and you take a derivative. It's a very easy mistake to make here. But you have to remember not to get tricked, and they just want average value of Bob's velocity. So the average value of Bob's velocity would just be 1 over 10 minus 0, because that was the interval they gave us, the integral from 0 to 10 of the Bob's velocity. Now Bob's velocity is up here. You got to make sure you use that function, not the derivative. Very easy mistake to make. And so we're going to, I'm actually going to write that in here, t cubed minus 6t squared plus 300 dt. And if we can evaluate this, we'll get Bob's average velocity. So what we wind up getting here is, it's not too bad. We have a 1/10 out front, and so I think we have enough room here. I'm going to write 1/10 times, and this is going to be t to the 4th over 4, minus, we'll add 1 to our exponent, divide by our new exponent here. I think we're going to get minus 2t cubed, and then plus 300t, and we're going to evaluate that from 0 to 10. Now, I can tell when I get to the 0 part, this is going to drop out, so all we have to worry about is the 10. And so this is going to be 1/10 times 10 to the 4th is 10,000. 10,000 divided by 4, that's going to give us 2,500. 10 cubed is 1,000 minus, or times negative 2 is going to be minus 2,000. And then 300 times 10 is 3,000. All right, so it looks like we have 2,500 minus 2,000 is 500. 500 plus 3,000 is 3,500. 1/10 of 3,500 would be 350. And this is his velocity, so it's 350 meters per minute. And there you go. So the entire question right here from A through D, and this graph's an important piece. So again, that's 2015 number 3, and we'll see you next time. Thanks.